Okay, so last time we were talking about the quasi-concavity, then the session ended abruptly. So let me continue. So you can imagine the third dimension here. Okay, so C1, C2, and there is utility, right? Now, if you draw it, utility is like a surface, right? If you increase C1 and if you increase C2, utility increases in that direction. So it is like this blue one is like a surface, okay? Now, in the regular preferences, in you know, convex preferences, convex in the sense that, you know, this upper contour set is convex, okay? So you have a very smooth edge here, okay? It's a very smooth surface. But in quasi-concavity, there are regions that are flat, okay? So here, there's a flat region. It's like the a road on the edge of a mountain, okay? Imagine a road on the edge of a mountain. So here, there are an infinite number of C1, C2 pairs, okay? Here, an infinite number of C1, C2 pairs that give you the same utility, okay? That's that same utility corresponding to that level, okay? So this is basically, you know, quasi-concavity, the logic of quasi-concavity, all right? So there are flat regions, okay? Now there is a nice way to check whether a function is quasi-concave. I will show you that. Okay, we're gonna look at the bordered Hessian of the function itself. Okay, so this is not the bordered Hessian that you saw in classical optimization theory. This is the bordered Hessian that is defined by first order and second order derivatives. So let me show you. If you have function f, you have f prime okay, for each argument you have these terms, then you have the transpose of it here, okay, f2 prime x f n prime x. So these are first order derivatives, and here on this part you have the Hessian. So second order derivatives, f11 x f12 x f1n double prime x. Okay, goes on like this. So at the end you have fnn double prime x. Okay, so this is the bordered Hessian that we're gonna use to see whether a function is quasi-concave. All right, I will show you later on. Now let me, do you have any questions about quasi-concavity? So there's a nice section in the text in the first chapter that explains all of these things. Okay, and again, as a cookbook procedure, I will show you the recipe of how to use bordered Hessian to understand whether a function is quasi-concave. Okay, then you're fine. But again, if you have questions, I can answer them. Now I want to go back to theorem 2.4. Okay, now suppose that f and gj functions are all quasi-concave. Okay, not concave, but quasi-concave. Then we have the following. So let me check. Then once again, Foc implies M, which means X star lambda star is a solution if one of the following is satisfied. Okay. First thing that we'll look at is this. So for some xi at the optimum, this will be negative. Okay. Okay. It could be at least just one. All right. So what does it say? If the derivative of the objective function at the optimum for some xi is negative and f and g's are all quasi-concave, then it is good. Or instead of quasi-concavity, we require that f prime x star is different than 0 and f is C2. So this means, this thing means twice continuously differentiable. Which means you can take not only the first derivatives, but the second derivatives of f as well. Okay? So you take the first derivative of f, these first derivatives exist, then you take the second order derivatives, and second order derivatives also exist. Okay? So this is another condition. Third, we have this. For some variable xi, we have positive derivative. For some xi, that is called relevant. So relevant means there is this x bar, okay, where g of x bar so just let me make sure. Yes. So g of x bar will be satisfied. So it will satisfy the inequality constraint plus x bar I will be positive. Okay. Now, why is that? What is that? Is this the Slater condition? Well, not exactly, but this is more about the satiation principle. Remember your micro theory? There is something called non-satiation. So our consumers are not typically locally satiated. So if you create a small increase, that will increase their utility, right? Now here, we want to look at points in the constraint set that satisfy the inequality constraint, points in the domain of the function that satisfy the constraint, and for some of them, okay, for that relevant variable, we have a positive derivative, which means that that variable is relevant in the sense that it increases your objective function. Okay? Usually, we are not going to be too concerned about these things because for at least one variable, right, we want to consume it. So if you actually look at the if you look at these conditions, you must realize that for many economic problems, at least one of them should be true, right? For many, not all perhaps, but for many. Why? Because especially the third one is very useful, right? Because we have those variables in our system which do not violate the constraint, which we consume positively. And for that relevant variable, of course, the derivative is positive. Okay? Because consuming more of it increases your welfare. So you are non-satiated. Okay? There is no satiation point. Because if that satiation point is on that flat region, then there is a problem. Okay? Finally, there is a third one if F is concave. All right? Now that also saves you a lot, right? Because if you know F is concave, but G's are quasi-concave, then this is solution. Okay? So theorems 2.2 and 2.4 gives you all the nice ways to check. Okay? Again, under quasi-concavity, if F and G's are not concave but quasi-concave, we require further conditions for second-order sufficiency. One is that for at least one variable, this derivative is negative. So at least one variable is a bad, not a good, right? At least one variable is a bad, not a good. Okay? Or around X star, so this must be around X star, the derivative of the objective function is different than 0, and F is twice continuously differentiable. And this is almost always satisfied in the economic problems, okay? And this depends on, of course, lambda as well, and G prime X as well, okay? Because we already know that, right? We already know this. Okay, I have a problem here. We already know this. From the Lagrange, I know that F prime X plus lambda G prime X star for some I, of course, is less than or equal to 0. Okay? In a typical consumer problem, for instance, this is negative. This is positive. So this is positive, right? So for many problems, we already know that it is different than 0, right? At the optimum. So this is usually satisfied. This is sometimes, perhaps, if you're a very, very interesting problem. This is also very useful. And if you already have concavity in F, that's a very nice thing already, right? Because then you can only check quasi-concavity of G functions. Okay? So that's the formal way of doing second order sufficient conditions. Now, last year, I didn't go over this theorem in detail, but since this is recorded, I'm trying to explain every single detail about this. So again, this is very useful for that. This is usually originating from preferences. Okay? Our preferences dictate some of the variables are relevant, and for these variables, we are non-satiated. Okay? And if you have this, then that's a great thing. Okay. So now let's solve some problems. Do you have any questions about this?
May I ask a question?
Yes, of course.
Based on theory 2.4, we have to satisfy all those 4 conditions?
No.
Right? Okay.
One of them.
One of them is most of the 2, right?
One of them is good.
The 2 one, I mean the second one, sorry.
No, not necessarily the second. Any one of them works, but this is usually true because if you are consuming a particular good, let's say in a consumer problem, then this is with equality, right? If you are consuming a positive amount, by first order condition, this is positive. Then if this is an income, if this resource is particularly about income, then this is negative, this is positive, this goes on to right hand side, and this is already satisfied.
Okay, thank you.
So typically in economic problems, these conditions are satisfied even if our functions are not concave. Okay?
All right. Thank you.
That's the point of this entire theorem. So again, most important work starts here, finding x star lambda star that satisfy first order conditions. Okay? Any other questions? All right, let's study a problem. So let's start here with a simple problem of utility, but here you will see a bit different. So suppose that people care about their consumption and also the bequest that they give to their children. Okay? Now this function, let's define it in this way. There is the consumption part and there is the bequest part. And let's assume that if an agent leaves no bequest to his kid or her kid, then utility is not negative infinity, right? Because if bequest would be 0, the utility could go to negative infinity, right? Remember logarithmic function. It's like this, right? So here, instead, we assume that there is some reference level, eta. So even if the parent does not leave any bequest, even if b is equal to 0, utility is still well defined. Okay? So the constraint is like this. First, I have my consumption. There's a price level I pay. Then let's say I have only one kid, so I will leave some bequest. Now this must be less than or equal to my gross interest plus my asset stock. Okay? So you can simply denote it as income. It doesn't really matter. Okay? And of course, consumption must be non-negative, bequest must be non-negative. You cannot leave a debt to your kid. Okay? Either you give 0 or you give a positive amount of bequest. you cannot leave a liability to your kid. Okay? So the Lagrange now is defined by my choice variables, as I have only one inequality constraint, right? So I have alpha ln c, beta ln b eta plus lambda income minus consumption expenditure minus bequest, right? Because this is now g of x greater than 0. Okay? Now, how do you proceed? Well, you're going to look at the first order necessary conditions, right? So, first, for your choice variables, then for your constraint. So, for choice variables, you have what? You have alpha, right? Divided by consumption, right? Let's look at one last time. So I'm taking derivative with respect to c. So alpha divided by c. Here it will be beta divided by b plus eta, right? So the derivative of the logarithmic functions. So then I have lambda p, okay? This must be less than or equal to 0. And c times alpha c minus lambda p must be equal to 0, and c must be greater than 0. Now I am dropping all the stars, okay? I'm dropping all the stars for simplicity. Then we have beta divided by b plus eta, okay, minus lambda, right? Let's look at the budget constraint, right? With respect to b, I have beta divided by b plus eta minus lambda, right? The derivative. Okay, so this must be, again, less than or equal to 0. Then b times this derivative must be equal to 0, and b must be greater than or equal to 0. Then for the constraint, I have what? G of, so I have only one g, sorry. I have income minus consumption minus bequest greater than or equal to 0. Then lambda times the constraint equal to 0, and lambda greater than or equal to 0. Okay? Now, we have 4 cases here, if you look at it carefully. 1, c equals 0, b equals 0. 2, c equals 0, b greater than 0. 3, c greater than 0, b equals 0. And 4, both of them strictly greater than 0. Okay? Now, exactly at this point, you should be seeing that 2 of them cannot be solutions. Can you explain why? Can somebody explain why?
Because c cannot be 0.
C cannot be 0. Why is that?
Because it goes to infinity.
Yes, if c is equal to 0, because of the utility function, because of this term, okay, the parent is punished, okay? If c goes to 0, regardless of the bequest, utility goes to negative infinity, all right? So you can understand quite simply that, okay, where is it? These two cases are then not optimal. But you can also see it in this way. Look at here. You know P is positive, right? Because this is price. You also know that lambda is non-negative. Okay? Now this condition tells you what? This condition tells you that alpha divided by C must be less than lambda P, less than or equal to lambda P, and lambda P is a non-negative number. Okay? So either it is positive number like 5, or it is 0, because lambda could be 0, right? But then, imagine what happens when C goes to positive, C goes to 0. If C goes to 0, alpha C goes to positive infinity, all right? And a number that goes to positive infinity is larger than any other real number. So this is violated. Okay? So that's the idea. For this reason, C equals 0 cannot be optimum. But by the very same reasoning, B equals 0 could be optimum. Why? Because this does not necessarily violate, is not necessarily violated if B is equal to 0. Okay? Because there is this eta term here. We allowed the parent to spend no bequest. But now we want to understand whether it is optimal or not. Okay? So how do you proceed? Well, you're going to check the two cases. Okay? So if B is equal to 0 and C is greater than 0, what do you have? You have alpha divided by C equals lambda P, right? Because C is greater than 0. Okay? And then you have beta divided by B plus eta less than or equal to lambda. Because, oh, sorry. Yes, because B is equal to 0. Okay? And you have the constraint. Constraint now looks like this. Okay, because B is equal to 0 again. Now, what is happening? Well, from this equation, you realize that lambda is equal to this, and it is strictly positive. Okay? If lambda is strictly positive, then you know that I minus PC must be equal to 0. So here you find C equals I divided by P, which is greater than 0, right? Now if you put C back into the lambda, right? You have lambda equals alpha P times P, so it is alpha divided by I, right? Now what happens here? If B is equal to 0, you have beta divided by eta less than lambda. So you have beta eta less than or equal to alpha I. Okay? If you rewrite this, you can find that beta less than or equal to alpha eta divided by income. Okay? So this is your consumption. This is your lambda. So let me rewrite it. So lambda is alpha divided by I. Okay. and you found it. You found C star, B star, lambda star that satisfy your first order conditions. Okay? Under the additional constraint that beta is less than alpha eta divided by I. Okay? Now, there is another case. Right? This one. This case is a typical consumer problem. There is no non-negativity now. So you have alpha divided by C equals lambda P, beta divided by B plus eta equals lambda, and I minus PC minus B equals 0. You have three equations. Three unknowns. Okay? So how do you proceed? Well, you can always do that, right? Alpha CP equals lambda, which is equal beta B plus eta. So here you eliminate lambda from the problem. Then you have PC plus B equal I, and alpha CP equals beta B plus eta. Okay? So this is a typical problem. In some values, at some values, so if this is B and this is C, sometimes your maximum will be, let's say, there, and sometimes it will be there. Okay? This is the earlier case. This is this case. So you can solve these two equations. And this solution gives you, again, C star, B star, and lambda star. And now the condition you will find will be this. Sorry. It will be beta strictly greater than alpha eta I. And you see the importance of this right now, right? What does it tell you? Remember what beta is. Beta is in the utility function, right? Alpha ln C, beta ln B plus eta. So if beta is sufficiently large, larger than this threshold, right? If beta is larger than this threshold, then B is positive. If beta, oops. If beta is sufficiently small, then bequest is 0. So it all boils down to the preference for bequest. Or you can do this. You can write this as this, then you tell if income level is sufficiently low, then there is no bequest. Okay, so you can interpret it in different ways. They're all relative, of course. Given your bequest preferences, you do not leave bequest to your kid if your income is low. Given your income, you do not leave bequest to your kid because you do not prefer it. Your preference for bequest is not strong enough. You are not altruist enough, for instance. you know, altruism. Okay. Now I'm gonna stop here, give you some assignments, not for credit, of course, for the next week, and then next week we're gonna continue with more examples. But I also finish in the next week I will finish this issue, this nonlinear programming issue, and start discussing dynamical systems in continuous time. So if you want to read the text before class, you can do it. Your assignments are, I want you to complete the solution of this problem. Okay. Let me direct you. So I want you to write C star, B star, and lambda star as a function of fundamentals. Okay, and these will be piecewise functions. Okay. Use theorems 2.2 and 2.4 to check second order sufficiency conditions. Okay, and work on this problem. I have less than 2 minutes. The class will end for today after I write this problem. So this is the problem of a master. Master provides one unit of labor, okay, and then there are apprentices. So this is master apprentice problem. So this 1 unit of labor is masters. These are apprentices. So this is the profit. Okay. So A is positive. Alpha is between 0 and 1. K is also positive, capital stock. And real wage is also positive. All right. Now solve this problem. These are your assignments. And as you see, I will start with a very simple assignment. All right. So next week, again, Wednesdays. Next week, Wednesday on 1 p.m. And please check the website as well. Okay. You can send me emails about your questions. Okay. It's about the end, so have a nice day.
Thank you very much.
Bye-bye.
Bye.
Bye-bye.